Hey, welcome everybody back to Lesson 5 in Algebra 2. This is Unit 10. Unit 10 is all about exponential and logarithmic functions. We began by looking at how to simplify and evaluate exponential expressions and then logarithm expressions. We talked about some important properties of logarithms as well. Today, we're going to look at how to graph an exponential and a logarithm function. Okay, so like I said, today we're going to be graphing exponential and logarithmic functions, and we're going to see that both of them are called asymptotes. So there are really two very important different kinds of asymptotes that we'll be talking about today. One is called a horizontal asymptote. A horizontal asymptote. And the other one is a vertical one. And basically, you can imagine the difference. One goes up and down, the vertical one that is, and the horizontal goes left and right. But it is important to remember that a vertical asymptote can never be crossed. So, vertical asymptotes absolutely never, ever, ever, for reasons that we'll learn more about in this unit and the next. Horizontal asymptotes actually can be crossed. So I don't want you to be thinking that you can't ever cross a horizontal asymptote. A horizontal asymptote can be crossed. They just typically won't be in this unit. So what exactly is this asymptote? Well, it's a line that you get closer and closer and closer to on the graph. And we often show asymptotes on a graph with dotted lines because they help you draw the shape of the curve. The curve will get closer and closer and closer and will approach it. Sometimes they get closer and closer while they cross over it over and over again. Other times, that would be horizontal. Other times, like with vertical asymptotes, they get closer and closer but never actually touch. So we'll see the different forms here and just some examples I have of different asymptotes. Now, to be perfectly accurate, we would need the equation, but given a graph, we can kind of estimate where an asymptote would occur, and we're going to use that to kind of get a feel for how these things work. So if you look at this graph here, it definitely appears that it's approaching the x-axis as I go to the left. So that is a horizontal asymptote. So we think, again, we really can't know for sure without the equation, but we think that there's a horizontal asymptote at y equals 0. Y equals 0 is actually the equation of the x-axis. Remember, all vertical lines are the form y equals. All right, all horizontal lines are y equals. Okay, let's take a look at this next one. Here's a vertical asymptote. This time the graph appears to be approaching this vertical line here that is the y-axis. And the y-axis is actually the equation x equals 0. So we have a vertical asymptote at x equals 0. All right, let's take a look at some more. Okay, on this one here, you can see that we have what appears to be a horizontal asymptote right here. Let me get my line tool there. So this one here, you can see the graph it approached, unlike the other ones, this one's approaching the horizontal asymptote in two directions. So it's approaching it to the left and to the right. So we have a horizontal asymptote, which we'll just call HA, at y equals 1. So we can see that a horizontal asymptote can be approached to one side, like as I go to the left towards negative infinity, or to the right, or to both sides. But it has to be approaching it as I go to an infinite x value. So it's not enough to just, we wouldn't say there's a horizontal asymptote here at y equals 5 because the graph approaches it. Because it approaches it and then goes away. It's not approaching it and getting closer as I go to the right or left. All right, this next graph has quite a bit of asymptotes. So we have another horizontal asymptote at y equals 0. You'll note that this asymptote is actually crossed. It's crossed, I picked the curve thing. I need the line. It's crossed, but that is actually okay on horizontal asymptotes. We won't see this in this unit, but we will see it in the next unit. But vertical asymptotes, of which it has two, those cannot be crossed. So these vertical asymptotes are not crossed by the curve. So I have two vertical asymptotes and one horizontal at x equals -2 and x equals +2. And I have one horizontal asymptote at y equals 0. All right, let's take a look at some functions now in the families we'll be studying. We'll be looking at exponentials and their inverses, which are logarithms. We're going to represent f of x equals 2 to the x with a table of values and a graph. So 2 to the -3, recall that a negative exponent means 1 over 2 to the third, which is 8. Excuse me, 1/8, though, because it's 1 over it. So this is 1/8. Likewise, this is 1/4, 1/2. Anything to the 0 power is 1. 2 to the first is 2, 2 to the second is 4, and 2 to the third is 8. Let's plot these points. So we have, over here at -3, we have something real small, and a little bit bigger, and then there. And then all of a sudden, it starts going really quickly upwards. So you can imagine that as I went to more and more negative values, I would just get small. I would just get 1 over a bigger and bigger number, which is actually a smaller and smaller number. So we're going to go up forever. And as we go to the left, though, we're going to get closer and closer and closer to 0. But we're never going to actually reach it. Because as x gets really small, like if x was maybe -100, then I'd have 1 over 2 to the 100th power. Well, that's a very, very small number. But it is still not exactly 0. So this is an asymptote that we don't actually touch. We just get really close to. So can we state the equation of the horizontal asymptote? Yes, we can. It's y equals 0. The domain, from the graph, you can see that this graph goes forever to the left, forever to the right. So it should make sense that our domain is all real numbers, or -infinity to infinity. That's my domain. But what about the range? Well, as we mentioned, it never actually reaches 0. So the range is just y greater than 0. Or in interval notation, we have a parenthesis around the 0, comma, infinity, because it's going up forever. All right, let's take a look at the next one. We're going to find f inverse. Recall that the inverse of f of exponentials are logarithms. So to find the inverse function of f, we need to remember that the inverse of this is a logarithm. Let me just write it again. Well, here was f of x, which is 2 to the x. So the inverse must be a logarithm. So the log base 2 of x, because that's what undoes exponentials. Well, we know how to graph this. We just need to flip-flop the points that we had. We had -3, -2, -1, 0, 1, 2, 3 for our x values. So now there are our y values. And this was 1/8, 1/4, 1/2, 1, and 2, and 4, and 8. So now let's plot those values. 1/8, -3. 1/4, -2. 1/2, -1. 1, 0. 2, 1. 4, 2. 8, 3. And this one's going to be giving me a little bit more difficulty to draw, I think, but I'll try. And there we go. Now, we learned that we cannot take the log of 0, so we're never going to be able to touch this vertical asymptote here, because we can't log 0, and we can't log negative numbers either. So the equation for the vertical asymptote is x equals 0, and my domain is 0 to infinity, and my range is actually -infinity to infinity. Remember that the range and domain of the inverse need to be flipped from the original, and they certainly are. All right, let's do another example. This time we'll start with the logarithm. Let's do log base 3 of x. Now, I've generated a few x values for us to use, but notice where I'm getting them from. These are simply powers of 3. And so remember, a logarithm is asking a question. It's asking the log base 3 of 1/9 is asking 3 to what power is 1/9? Well, it needs to be a negative number to give me 1 over, and in this case, it needs to be a -2. Then 1/3, 3 to negative 1 is 1/3. 3 to the 0 is 1. Remember, the log of 1 is always 0. 3 to the first is 3, and 3 to the second is 9. And now we can plot these values. So 1/9 is at negative 2. 1/3 is at negative 1. 1, 0, 3, 1, 9, 2. And there we have it. It kind of just zooms down here. It goes straight down like that. The vertical asymptote, again, is x equals 0. The domain is 0 to infinity, and our range is negative infinity to infinity. The inverse of, remember, let me just write this again. It was log base 3 of x. So the inverse would be the exponential 3 to the x. And we can, go ahead and put these same x values that we've been using. This time I'll just do negative 2, negative 1, 0, 1, 2. 3 of the negative 2 is 1/9, and that's 1/3, 1, 3, and 9. And so now we get this shape for the inverse. And notice they are indeed reflections across the line y equals x, and the x and y coordinates are swapped from our original one. Okay, here we go. All right, horizontal asymptote, y equals 0. Domain, negative infinity to infinity, because I can raise an exponent to any real number power. Range, I can raise a 3 to any real number power. You can use any exponent. And the range is 0 to infinity. All right, I got a practice problem for you to do. Would you please fill this out and see if you can't go through this whole process again of generating an exponential and a logarithm that are related. Okay, let's see how you did. So remember that log, when it doesn't say the base, is base 10. So the log of 1 over 100 is negative 2. This is negative 1, 0, 1, and 2. So the log base 10 is a very sharp turn. Very sharp. See, we at negative 2 on the y, we're already down here at 1/100th. So it turns very sharply. 1/10, maybe that, and then here, then I got to go all the way out to 10 before I go up to 1. So it makes this really sharp curve, sharper than that. Yeah, something like that. Grows very slowly. So the vertical asymptote is x equals 0. The domain is 0 to infinity, and the range is negative infinity to infinity. The inverse of log of x is 10 to the x. And we can represent that. Again, I'll just use, these are when you're doing an exponential, negative 2 to 2 are good numbers to start with. So 10 to the negative 2 is 1 over 10 squared. 10 to the negative 1. Anything to the 0 is 1. And we can see how this works out. So it's really just the same points, but we just flip-flop the x and y values. So now it goes up really quickly. We have a horizontal asymptote this time of y equals 0. A domain of negative infinity to infinity, and a range of 0 to infinity. All right, what I'd like you to do is just practice a few more questions. Let's see here. I got one more like this, and then we're going to go on to just practicing graphing. I think it's a good point for you to just work on all this yourself, and then we'll pause the video and go over it. Of course, you can always pause it and work one at a time if you like. All right, and like I said, I'm just going to go through the rest of these now, and we'll see how you did. 4 to the negative 2 is 1/16. This is 1/4. 1/416, which works out to be this curve going through 0, 1, and then accelerating upwards very quickly. Has a horizontal asymptote of y equals 0. A domain of negative infinity to infinity, but a range of 0 to infinity. The inverse, since we're doing 4 to the x, is log base 4 of x, which will have all those points flip-flopped. So we had 1/4, 1/2. No, that's not true. We had 1/16, 1/4, 1, 4, and 16. This is -2, -1, 0, 1, and 2. And let's plot them. So you can see it's very similar to shapes we've already seen. It's just a little bit less dramatic of a right turn. Something kind of like that. It does continue to increase. It's not an asymptote on the horizontal, but there is a vertical asymptote at x equals 0. The domain is 0 to infinity, and the range is -infinity to infinity. Okay, now you're tasked with graphing these all by yourself. But you could still make a table of values. -2 to 2 is always a good set of numbers to experiment with. 2 to the -2 is 1/4. 2 to the -1 is 1/2. 2 to the 0 is 1. 2 to the first is 2. And 2 to the second is 4. And there we go. Okay, let's do another one. We're going to do the log base 5 of x. So for the x's, I need powers of 5. How about 1/25? 1/5, 1, 5, and 25. The log base 5 of 1/25 is a -2. The log base 5 of 1/5 is -1. The log base 5 of 1 is 0. Log base 5 of 5 is 1. And log base 5 of 25 should be 2. So it goes something like this. Then it goes through 5, 1, and keeps going like that. Okay, 6 to the x. Again, you can use -2 to +2. It would work nicely. That's 1/36, 1/6, 1, 6, and 36. And hopefully you're seeing kind of these patterns develop. That key point, it's always going to go through 1 on the y-axis for these exponentials, and then whatever the base is, that's what it'll go through when the x is 1. And then it just kind of goes to the left and goes up. Log base 2. So we can do powers of 2 now. About -1, or excuse me, just 1/4, 1/2, 1, 2, 4. Maybe you want 8 as well. Something like that. All right, there we go. All right, so for x to take, I want you to take a second and consider this. What is an asymptote? How are the asymptotes of y equals 2 to the x and log base 2 of x similar? And how are they different? Well, the answer is the asymptotes for y equals 2 to the x are horizontal, and for log base 2 of x are vertical. But they have the same numeric value. The y equals 2 to the x has an asymptote of y equals 0, but the other one is x equals 0. Same number, but they're written differently because one's horizontal and one's vertical. And that's pretty much what I want you to get from that.